Hi Year 12. This is the second video for the topic Statistical Analysis for Extension 1 Mathematics. In this lesson, we're going to look at binomial distribution. In the last lesson, we learnt about Bernoulli random variables and Bernoulli trials. So, a binomial distribution is formed from repeated Bernoulli trials. And remember, a Bernoulli trial has two outcomes, success and failure. And this is what we write. X is distributed as binomial with n trials and p is the probability of success. Let's look at an example. A biased coin is tossed 3 times and the number of tails is recorded. It is twice as likely to land tails as heads. So let's look at the sample space. If it's twice as likely to land tails, that means we've got 2 tails for every heads, which means the probability of success is going to be 2/3 and the probability of failure is going to be 1/3. What is the probability that there are no tails? So that means we're going to throw heads, then heads, then heads. So that is 1/3 times 1/3 times 1/3, or 1/3 cubed. What's the probability? There's exactly one tail. So there's 3 ways we can get that. We can have tails, heads, 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 tails, heads, or heads, heads, tails. If I write it all out, it looks like this. Bit of a nightmare, isn't it? So we've got 2/3 times 1/3 times 1/3 plus 1/3 times 2/3 times 1/3 plus 1/3 times 1/3 times 2/3. Or they're all actually the same, they're just in different orders. So 3 times 2/3 to the power of 1, 1/3 to the power of 2. Exactly 2 tails. So we can have tails, tails, heads, tails, heads, tails, heads, tails, tails. Again, quite complicated. They're all going to be the same. They're just in different orders. So there'll be 3 lots of 2/3 squared times 1/3. And finally, 3 tails. So tails, tails, tails. That's going to be 2/3 cubed. Now my question is, can you see a pattern? Let's look at it more closely. We're saying that X is distributed as a binomial distribution with 3 trials. The probability of success is 2/3. The probability that we get 0 successes is 1/3 cubed. The probability we get 1 success is 3 times 2/3 times 1/3 squared. The probability we get 2 successes is 3 times 2/3 squared times 1/3. And the probability we get 3 successes is 2/3 cubed. Now, you can probably see where all of these come from. This is the probability of failure. We want 3 failures. Here we want 1 success, 2 failures. So 1 success, 2 failures, etc., etc. But where do these numbers come from? This 3 and this 3. Well, actually from Pascal's triangle. And it's this line here. 1, 3, 3, 1. There's the 3's. And remember that this is 3C0, 3C1, 3C2, and 3C3. So I've changed these just to add a little bit more information. So probability that we get 0 successes, 3C0, that's the number of ways we can order 0 successes in 3 trials. 2/3 is the probability of success to the power of 0. 1/3 is the probability of failure to the power of 3. Here we've got the probability of x equals 1, so 1 success. How many ways can we order that 1 success? 3C1. Probability of success, probability of failure. Here we've got 2 successes. This is the number of ways we can order those 2 successes. Here's the probability of success, the probability of failure. And finally, x is equal to 3, 3 successes. It's going to be 3C3, probability of success cubed, probability of failure to the power of 0. And just in case you're interested, these expressions all come from expanding this using our binomial theorem. That's why we end up with all of these coefficients here. So here's our formula. If P is the probability of success and 1 minus P is the probability of failure, then the probability of R successes in N independent trials is given by probability of R successes is NCR multiplied by p to the power of r multiplied by 1 minus p to the power of n minus r. Here's an example. If I throw 5 dice, what is the probability of throwing 3 sixes? Right, with these sorts of questions, we always start by working out the probability of success. Throwing a 6 is considered to be a success, and the probability of throwing a 6 is 1/6. Now let's work out the probability of failure. It's just 1 take away 1/6, which is 5/6. Now let's use our formula. The probability we throw exactly 3 sixes. This is the number of ways that we can order the 3 sixes in the 5 dice. Here's our probability of success. We want 3 successes. Here's our probability of failure. We want 2 failures. Into the calculator, we get 0.032. The probability that we throw at least 1 6. So that's 1 6, 2 6s, 3 6s, 4 6s, or 5 6s. But remember, when you see these words at least, we should consider the complementary event, which is going to be much easier to work out. So the probability that we throw at least 1 6 is exactly the same as 1. Take away the probability that we throw no 6s. And we're going to use our formula here. So it's going to be 1 take away. Out of 5 throws, we throw 0 6s, probability of success to the power of 0, probability of failure to the power of 5. So let's talk about the mean and variance of a binomial distribution. Now remember, a binomial distribution consists of n Bernoulli trials, and in each trial, the mean is p. So the mean of a binomial distribution is given by this. So expected value of x, that's our binomial distribution, is going to be equal to the expected value of all of these Bernoulli trials means added up. Now this is equal to this, and that's something we actually haven't learnt yet or proven, but it's quite logical. Consider that you've got a random variable x, say, and the mean is 2. So I'm just going to put it up here. And then you've got another random variable y, and the mean is 5. It's logical that the expected value of x plus y must be the expected value of x plus the expected value of y. So this is true. Hence I can go from here to here. Now we know that each one of these, the expected value is p. And there are n of them, so the expected value of our binomial distribution is np. And variance can be thought of the same way. The variance of our binomial is equal to the variance of each of the individual Bernoulli trials added together. We can rewrite that as variance of x1 plus the variance of x2, etc. Now, we learnt that the variance of a Bernoulli random variable is p multiplied by 1 minus p. And there are n of them. So this gives us our formula. np brackets 1 minus p. Here's an example. A die is tossed 60 times and the number of sixes is recorded. Find the mean and variance of this distribution and describe the shape. Alright, so let's just use our formulas. Expected value of x is n times p, so it's going to be 60 times probability of success, which is 1/6. So our expected value is 10. If we toss the die 60 times, we're expecting 10 sixes. The variance, here's the formula. So n times p is 10, and then 1 take away 1/6, which is 25/3. And then it asks us to describe the shape. So on Excel, I just simulated that experiment just with random numbers. And after 60 trials, it kind of looks like a normal distribution, doesn't it? Which begs the question, what happens to the shape of a binomial distribution with different values for n? So here's 10 trials, 60 trials, 100 trials. Can you see as n increases, the shape of the distribution becomes more normal? How about different values for p? So I've got 60 trials in each case. Probability of success is 1/6, 1/2, and 5/6. So when it's a half, it's pretty symmetrical. Here we have a slight positive skew. Here we have a slight negative skew, which leads us into normal approximation of a binomial distribution, which is our next lesson.